Hello, and welcome to the video accompaniment for Chapter 2, Section 2 of our text, entitled Set Operations. And I thought I'd do something a little bit different for this video because there's a lot of drawings that would take time for me to do by just drawing on the slides. So instead, in this one, I have them all drawn out, and I'll just go through this like a PowerPoint presentation. You should know there is an activity. I didn't have activity alert pop up, so I'm just going to do that real quick. Activity alert. Activity alert. There will be an activity problem in this video later on. And I'll mention that when we come to it. In this section, we see a lot of different set operations. The first two that we encounter are union and intersection. So I think it'll be useful to just go through these definitions and a couple examples of them to make sure you have it. So given two sets A and B, the union of A and B, written A cut B, is a set of all elements belonging to at least one of A and B. So in order to be in the union, you just have to be in A or you have to be in B. That is, A union B is the set of all X such that X is in A or X is in B. And it looks like this. A and B are these blobs, right, using the Venn diagrams, and the shaded region is A union B. So everything that's in A and everything that's in B is all included in A union B. An example of this, what if A is 1, 3, 5, and 7, and B is 2, 4, 6, and 8? Then the union of these would be all the elements that are in either A or in B. Therefore, A union B would be the set 1, 2, 3, 4, 5, 6, 7, 8. The other operation we encounter first is the intersection of A and B. A cap B is how it's notated, and this is the set of all elements belonging to both A and B. So in order to be in the intersection, you have to be in A and you have to be in B. Hence, A intersect B is the set of all X such that X is in A and X is in B. That looks like this in a Venn diagram. Again, there's A and B. The shaded region is A intersect B. It's the elements which are common to both A and B. An example of this, A is 1, 2, 3, 4, 5, 6, 7, and B is 7, 9, and 1. Then the intersection would be everything that's common to both of them. So just the elements 1 and 7 are in both sets, and so that's the intersection. Remember that with statements, so our objects were statements, we had an operation on those things called conjunction and disjunction. And along with those operations, we had laws that told us how they work. So same thing is going to be true here with union and intersection. With statements, with disjunction and conjunction, we had a theorem that described the laws. This one for sets is going to involve three arbitrary sets A, B, and C. And with statements, we had the commutative laws, we had associative laws, and we had distributive laws. Now, since union and intersection are defined in terms of disjunction and conjunction of specific statements, those laws are going to transfer over. The laws of statements will transfer over to the laws of sets. So we'll have these commutative laws, A union B is B union A, doesn't matter what order we write them in, and one for intersection. We'll have an associative law for unions, which tells us it doesn't matter how we group them, and so it's really, if we're just dealing with a bunch of unions, we don't need to write parentheses. And something similar for intersections. And lastly, we have the distributive laws, that intersection distributes over union, and union distributes over intersection. I want to stress this point that anytime we're dealing with a new set of objects, like sets, and operations on those objects, union and intersection, we don't get to assume that these laws are true. We really have to prove that these laws are true by using their definitions. And this is true anytime we have a new set of objects and a new set of operations on those objects. We can't take these for granted. We need to first understand why they're true and establish that they're true, because these aren't always going to be true. So let's take a look at each one of these and see why it's true. So why? The commutative law of union. We'll just focus on union because the intersection commutative law is proved very similarly. So commutative law of union, we know that the definition of union is that it's the collection of all x such that x is in A or B. So here I'm just writing the definition of union out. So notice I'm starting with the statement that describes what it means to be an element of the union and then writing out what the definition for that is. So now we have definition of union down, x is in A or x is in B. And then remember, now that it's in terms of statements, we can switch the order of those because we know that that disjunction is commutative. And so it's okay to switch the order. We know that those are equivalent statements. And now we can build our way back up to sets. X is in B or X is in A. Well, that's the same thing as saying X is in B union A. That's the definition of union. And so what we have here in conclusion is that A union B is equal to B union A because the statements which define them are equivalent. That's the idea. Now we can also see that this is true by using Venn diagrams. So here's A union B, and here's B union A. And clearly those two things are exactly the same. There's no difference between these two, and so they're equal. So why, again, why does the associative law of union hold? Remember this says that A parentheses A union B union C is the same thing as A union parentheses B union C. So again, we'll start with the left-hand side here and just write down what it means to be an element of that union. So X is in A union B union C. So just like we did with the last one, let's break this down into statements, use properties of statements, and then build it back up to sets and see what we get. So if X is in this set, by definition of union, that means X is in A union B, or X is in C. So that's definition of union. And we have another union there we can break down. X is in A union B means X is in A or X is in B. So we have X is in A or X is in B, or X is in C. But we know that with statements, it doesn't matter, right? If we're just using disjunction, it doesn't matter where we put parentheses, it'll be the same regardless. And so we can switch those parentheses around and write X is in A or X is in B or X is in C. And so now we're using the associative law of disjunction. Now we'll build our way back up to sets. X is in B or X is in C, that means X is in B union C. Definition of union again. And now we have another or statement here that we can build up to a statement about sets. So X is in A union B union C. And so in conclusion, since the underlying statements are equivalent that define the two sets must be equal. Again, we can see this with Venn diagrams. Here's A union B. I'll take that and I'll union that with C to get this set. So that's the left-hand side is A union B union C. And on the right-hand side, we'll take B union C and perform a union with the set A to get this set. And again, we can see that the two sets we ended up with, the left-hand side and the right-hand side, are both equal. So why is the distributive law true? In this one, we're going to look at the reason why intersection distributes over union. So again, we'll start with X is in A intersect B union C, and we'll decompose this into statements, use properties of statements, and then recompose it into sets and see what we find. So X is in A and X is in A intersect B union C. This is the same thing as saying X is in A and X is in B union C. That's the definition of intersection. Now we'll use the definition of union and break that down. X is in A and X is in B or X is in C. That's the definition of union. And now, if you can see it, we have conjunction distributing over disjunction. We have a conjunction of the statement X is in A over the statement X is in B or X is in C. And so we can apply the distributive law of logic to rewrite this. This is equivalent to X is in A and X is in B, or X is in A and X is in C. And now we'll build up those. Now we'll build that back up into the language of sets. X is in A and X is in B. That means X is in A intersect B. X is in A and X is in C. That means X is in A intersect C. So we built those up, and now we still have a disjunction hanging around, so we can build that further up into sets and see that X is in A intersect B, or union A intersect C. And so since the underlying statements are equivalent, these two sets must be equal. So intersection distributes over union. And again, we can look at Venn diagrams to see why visually this should be true. So we'll start with B union C, and then I'll intersect that with A. So there's A intersect B union C. That's the left-hand side. Now I'll look at the right-hand side. We have A intersect B, and we have A intersect C, and then we can take the union of them to get to the right-hand side. So take the union of those two sets. The shaded region should have all the things that shaded in the first one and all the things that shaded in the second one. And so there's A intersect B union A intersect C. And we can see that the left-hand side and the right-hand side now are equal, that those two sets describe the exact same thing. So while we can do the union and intersection of just two sets, since we have associativity, it doesn't matter how we group them. It means that taking a union of a bunch of sets is well defined. We don't need to draw any parentheses there because we know that parentheses don't matter when we just have a bunch of unions. So that allows us to take a union of a collection of sets. Same thing with intersection. So here we'll let n be a natural number, and for each integer I, where I is between 1 and n, let ai be a set. Okay, so we have the sets A1, A2, A3, all the way up to AN. We have that collection of sets. That's what that's saying. Then the union of all these sets is the collection of all elements that are in at least one of the sets, just like how it's defined for union. And in the intersection of all these sets, these A sub i's, is a collection of all elements that belong to all of the sets. So each element in this intersection of the AI's will belong to each AI. So this is notated as follows. With the union, it's a big union symbol from I equals 1 to n. So that's specifying which sets or how the index works here. And then the A sub I there is telling me which sets I'm taking the union of. So I'm starting at I equals 1, and I'm going I equals 1, I equals 2, I equals 3, all the way up to I equals n. And I'm taking the union of all those sets. I could also write that using an ellipsis by saying A1 union A2 union ... AN. Or I could describe it using set builder notation. It's the set of all x such that x is in A1 or x is in A2 or ... x is in AN. Similarly with intersection, we'll use a big cap and we'll take the intersection of the AI. We could write it with an ellipsis, or we can write it using set builder notation. X is in A1 and x is in A2 and so forth. X is in AN. So let's look at an example here. Here we'll let the AI's, we'll let AI for each I, we'll let AI equal the set of integers between I and I plus 5. And we'll pick 6 of these. We'll do this up to n equals 6. And so we'll have the sets A1 will be the set of elements between 1 and 1 plus 5, 6. So A1 is 1, 2, 3, 4, 5, and 6. A2 then will be the set of all integers between 2 and 7. 2, 3, 4, 5, 6, 7. And we can do this for each I between 1 and 6. Lastly, we'll get the set A6, which is 6, 7, 8, 9, 10, and 11. Now let's compute the union of all these sets along with the intersection of all these sets. So the union of the A sub i's will be the set 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and 11. Why? Because each one of those elements there belong to at least one of the A sub i's. And we could also describe that big union using set builder. It's the set of all integers between 1 and 11. Now notice here, we don't double up on any elements. I haven't mentioned this yet, but sets never have repeated elements in them. Each element in the set is distinct from the other ones, and you can't have two of the same element in the same set. When we do the intersection of the AI's, we want to just find all those elements that are common to every set. So in order to be in the intersection, you have to be in all of the AI's, and the only integer here that does that is the integer 6, is in every single one of the AI's. Everything else is not in one of the sets. So like, for example, the element 1, it may be in A1, but it's not in A2, and so it's not in the intersection. It has to be in all of them. Now that we've talked about union and intersection, we can define two new set operations called difference and symmetric difference. So again, we'll start with A and B just being arbitrary sets. The difference, A minus B, is the set of elements in A, but not in B. That is, it's the collection of all elements X in A, such that X is not an element of B. So what this means is we'll take the set A and we'll remove all those elements from it that are in B. And that will leave us with A minus B. Now this is our first non-commutative binary operation on sets. A minus B is not in general the same thing as B minus A. Let's take a look at an example and compute a subtraction of sets. So A is the set of all integers between -2 and 2, and B is the set of all integers between 0 and 4. Let's figure out what A minus B and B minus A are in this case. So A minus B, A is the set of elements -2, -1, 0, 1, and 2. And if we take away all those elements that are in B, so 0, 1, 2, 3, and 4, what we're left with is just -2 and -1. Now notice that B had some elements that A didn't have, and we didn't say right, like for example, 3 is in B, but 3 is not in A. We didn't write -3 in A minus B, right? We didn't really do anything with that. We just sort of ignored those because they weren't in A. Remember, A minus B should be a subset of A. Everything in A minus B is an element of A that's not an element of B. Similarly, we can do B minus A. B has the elements 3 and 4 in it, which A does not have. But the other elements in B, 0, 1, and 2, are also elements of A. And so we peel those off to get B minus A. And so here we can see that A minus B and B minus A are not the same thing, right? There is no commutative law for set subtraction. So it's a non-commutative operation. What this looks like in terms of Venn diagrams is this. Here's A, here's B, here's A minus B, the stuff that's in A, but not in B. And here's B minus A, the stuff that's in B, but not in A. Along with this is something called the symmetric difference of two sets, and here we use the O plus symbol, which you should recognize that we used for XOR, the exclusive OR operation of statements. So sometimes with sets we use the triangle. In this class we'll use the O plus rather than the triangle, but you might see the triangle somewhere else as for symmetric difference. So this is defined to be the set of elements that are in either A or B, but not both A and B. That is, it's this. X, it's the set of all X, such that X is in A or X is in B, and it's not the case that X is in A and X is in B. So we remove all those ones that are in A and B. And so notice that this is the same thing as the exclusive OR operation between statements. We could write this as the set of all X such that X is in A, XOR X is in B. If we wanted, we could use that symbol, like that. So let's take a look at an example with these sets A and B and compute the symmetric difference of A and B. And notice that symmetric difference is commutative. It doesn't matter which order we write the A and B. So with A and B defined there, symmetric difference of A and B, so that we take the set of all those elements that are in A or B, so that would be the integers between -2 and 4, and we remove those ones that are common to both A and B. That is, we remove the intersection of A and B. Intersection of A and B is 0, 1, and 2. And so when we take the union and remove the intersection, we get the symmetric difference, in this case, -2, -1, 3, and 4. Now there's another way to describe this in terms of difference of sets. So we'll look at a Venn diagram to see that. So here's what the symmetric difference looks like in general. Stuff that's in A, stuff that's in B, but not the stuff that's in both of them. And look at the relationship between that set and the two differences that we have on the left there. Notice that if I take the union of those two sets, A minus B and B minus A, I get this set, A minus B union B minus A, which is the same as the symmetric difference. So this would be another way to define the symmetric difference. And in fact, there's several ways to do that. With statements, we had what's called a unary operation on statements, which was negation, right? We didn't take the, right, negation wasn't an operation between two statements. It was just an operation on a single statement. That's called unary. It operates on a single object. So the parallel, or the analog of that for sets, is the idea of the complement of a set. So the complement of a set A is a set of all elements in the universal set which are not elements of A. And we write that with just an overline on the A. So overline A. Since this definition depends on what the universal set is, right? It's a set of all elements in the universal set that aren't elements of A. This is going to depend on what the universal set is, and so we'll have to be very careful that that's clearly defined or given to us. So we can define this using set builder. The complement of A is a set of all x in the universal set such that x is not in A, or we could define it as the set of all x in the universal set such that it is not the case that x is in A, if we want to write it like that. Those are equivalent. Right, so I said it's a unary operation, and it's similar to negation. And we need to take care that the universal set is clearly defined. So as an example, we'll take the integers to be the universal set. We'll take E to be the set of all even integers. Then the complement of E is the set of all integers that are not even, which is the same thing as the odd integers. So the complement of the even integers is the odd integers when the universal set is the integers. What a complement looks like with a Venn diagram is this. Here's the universal set. It's the big rectangle. A is the blob in the middle. Then the complement of A is everything that's outside of A. So what I'd like you to do now is work through the problem in the activity. Here's an activity alert for you. Let A and B be subsets of some universal set. We want to be able to express the complement of union in terms of the complement of A and the complement of B, and we want to be able to express the complement of an intersection in terms of the complement of A and the complement of B. And it'll be helpful to draw Venn diagrams for these, and if you work through that activity, that'll sort of help you figure out what it is. In the next slide, I am going to go over that activity. Right, here's A union B. And here's A intersect B. I'm asking you to find what the complement of A union B is and then express that in terms of A complement and B complement, and similarly for A intersect B. Figure that out. So take a second to work through that activity and join me when you're done on the next slide. So let's just go over what you did in that activity. Here's A intersect B, here's A union B, here's the complement of A union B, and we'd like to express that complement in terms of the complement of A and the complement of B. So notice that A complement looks like this, and B complement looks like this. We can draw those. And then we want to figure out how can I combine those, A complement and B complement, to get the complement of A union B. And the magic operation that works here is the intersection. If we just take what's common to A complement and B complement, what we get is this set, A complement intersect B complement, which is the same as the complement of A union B. So we can do that using Venn diagrams. We can also see how this works using logic. So X is in A union B complement is the same thing as saying that X is not in A, or same thing as saying it's not the case that X is in A or X is in B, right? It's the stuff that's outside of X is in A or X is in B. It's the elements for which that's not true. And now what we can use is De Morgan's law of logic to distribute that negation over the disjunction and get a conjunction of these two statements. which just means that X is in A complement and X is in B complement. Writing that in terms of sets, X is in A complement, intersect B complement. And so these two sets are equal. Notice that we use De Morgan's law to rewrite the logic here, and in fact, this is called one of De Morgan's laws of sets. So we have De Morgan's laws for logic, which tell us how to distribute negation over disjunction and negation over conjunction. Here we have De Morgan's laws of sets, which will tell us how to take the complement of a union and how to take the complement of an intersection. So here we have the complement of a union defined as the intersection of these two complements. So we'll do the same thing now with complement of A intersect B. That looks like this. And now we want to figure out how can we combine A complement and B complement to get that set. Well, if we take the union of them, stuff that's in either A complement or B complement, we get this set, which is the same thing as what we started with. I missed an equal sign there, but those two sets are equal. Let me actually draw that in real quick to avoid any kind of confusion. I'll just draw. Sorry, sometimes I lose my pointer. These two sets are equal. And we can do the same thing with logic to prove that this is true. So X being in the complement of A intersect B means X is that it's not the case that X is in A and X is in B. And then we can use De Morgan's law of logic to distribute that negation across the conjunction to get a disjunction of these two, which means X is in A complement, or X is in B complement, which is just the union of A complement and B complement. And that tells us our second of De Morgan's laws of sets, what the complement of A intersect B is in terms of complement of A and complement of B. So for all of these things we've been proving, there's always a logical side to it as well as a visual side to it. Venn diagrams versus laws of logic.